Okay, guys. Thank you for having me here. My name is Emilio Frangella. I work in Aave. I work as a community contributor. I worked before for Aave companies as a smart contract lead engineer. And I'm currently contributing to the community I co-founded with other core Aave developers, BGD Labs, which focuses on contributing to the Aave ecosystem through core smart contract developing. So what I want to talk about today is a quite interesting topic that for me, it has been is something that is very humbling when we write smart contract code. And it's about like how very, very simple mistakes can actually have even devastating consequences when we write smart contract software, and in general, what we call mission critical software, right? So let's start. Why smart contracts are mission critical software? Well, here we can see like this tweet by Token Terminal actually shows how in the last 2 years, more or less, more than 4 billion worth of assets have been stolen through vulnerabilities, abuse, and smart contract hacks, right? So like 4 billions is actually a lot of money, right? And this is a very, very important topic for our space. And it's something that, of course, we need to solve in the proper way, because users impacted by hacks are users that, in general, many of them, like they use these technologies, these smart contracts daily. Many of them with important parts of their net worth, and losing an important part of your net worth can have disrupting impact on your life, right? So all of this, all that we do in DeFi has impact on people's lives. So this is very, very important for to scale our industry and also to provide reliable software, reliable decentralized software, right? So why are smart contracts mission critical software? Well, one of the reasons I just explained, the fact that they impact people's lives and they can disrupt people's lives. Another aspect is that, like, inherent to the technology itself, and is because mostly the nature of smart contracts, the immutability of smart contracts, or the fact that they are governance controlled, which means that it's really, really hard to fix bugs, right? So if a smart contract is immutable, you're not gonna be able to fix any bug. And if they are governance controlled, there is usually a delay to any smart contract upgrade that is usually enough for attackers to still attack the system, even if we know where the bug is and what the potential fixes are. And not only that, but the nature of the environment we work in, like the nature of the Ethereum blockchain, and the nature of the EVM and the actors that play in DeFi, it's very adversarial, right? So all of this kind of exacerbates the problem of making smart contracts as safe as possible. So how do we make them as safe as possible? Well, I would say that the key here is the processes that we follow when we write smart contracts, right? And when we develop this kind of technologies. So let's make a parallel with a real world example, right? If someone follows me on Twitter, they probably know that I am a huge space nerd. I love space, I love astrophysics. And like one example that for me is pretty explanatory of what I mean with mission critical software is this particular case that happened to NASA in 1999. So essentially, NASA lost a 125 million worth probe, an orbiter, because part of the team was using the metric system to measure distances, while other part of the team was using the imperial system, right? So essentially, this was a human oversight that made the prober ultimately useless. It was impossible to drive it, so the whole developing process and the whole budget allocated for the process was ultimately lost. What I find particularly interesting are like the quotes of Edward Whaler, that is one of the engineers of NASA. Like, people sometimes make mistakes, like they make errors. This is unavoidable. Unfortunately, it's part of the human nature. So the real problem here is not the error itself, is the inability or the failure to capture this kind of errors, right? So essentially, a failure in our processes to detect the error, which is, I think, what is really important here. So we have just seen a real-life case of like, you know, failure in processes to detect even trivial, sometimes, error. Now, when I say trivial, people could argue that they are actually not trivial, that are really bad mistakes. I don't disagree. When I say trivial, I mean that they can be human oversights that are, unfortunately, for what the human nature is, they are pretty easy to manifest, but they are really hard to catch. So in hindsight, they might look like really bad mistakes, but in reality, they are oversights that sometimes they are quite easy to slip in your processes, right? So I wanted to choose a parallel with what happens with you know, smart contract development in DeFi, usually. I took two examples. There are many, honestly, and unfortunately, like many occasions in this space where trivial errors actually caused like the loss of hundreds of millions of dollars. I choose two that, in my opinion, are particularly meaningful. One is specifically for Aave, so it was a failure of our process, of my process. I was working on the project, so it was a lesson for us on how to improve our project, our processes. Another one, for the nature of it and the way it actually ended up being on production code, is the, probably some of you guys will remember, is an accounting error that affected one of Compound proposals, which caused like the system to lose about around 80 million worth of comp tokens. So let's dive quickly into them. Like, this is like the Compound liquidity mining accounting error. Unfortunately, this is a very, very small mistake. The mistake here is in the condition above, the first line. The greater symbol should have been greater or equal, right? So unfortunately, because of this very, very small oversight, there were some markets on the Compound protocol in which liquidity mining was not actually active, which made essentially the accounting index for the liquidity mining being equal to Compound index, which means this whole block of code was skipped when the proposal was executed. And the supplier index was not initialized properly, which means that people started getting way more comp rewards that they should have got. And this caused essentially the loss of 80 million worth of comp tokens, if I remember correctly. But that is not the topic. The topic is like how small the error actually was, how like narrow was the particular case of the edge case that the code didn't handle because of this mistake. And despite that, like the consequences were kind of devastating, unfortunately. And this is also interesting because this was added through a governance proposal. So a governance proposal that was executed after the protocol was actually live, introduced the mistake which I will essentially reconnect after when I will talk about the processes and how to handle like upgrades of code, actual production code, like in this case. The other mistake is actually related to Aave specifically. It's interesting because this vulnerability was live for 1.5 years before it was discovered by one of the Trail of Bits engineers and security engineers. So thankfully, nobody abused it, but this would not have caused a loss of funds, but would have caused like disruptive denial of service. essentially what could have happened is that one of the key smart contracts of the Aave protocol could have been by manipulating the way the contracts were deployed and initialized or non-initialized in this particular case. An attacker could have forced one of the main protocol contracts to be to self-destruct, which essentially would have disrupted the system for 4 days, which is the time delay of the governance, which requires 3 days of voting plus 1 day of time lock. So in this particular case, this was our failure of reviewing processes of deployment of production-ready code. So there was an oversight when we deployed this code in production, which essentially could have caused a massive disruption of the system, even though there was technically no loss of funds involved, but the system could have essentially been disrupted for 4 days. And it's honestly, the way that the vulnerability was unveiled was similar to the Parity hack. I don't know if some of you guys will remember, where essentially a key smart contract of the Parity wallet was forced to be destroyed through the same kind of attack. So here, I put a bit of the code that shows how the vulnerability actually worked. Essentially, one of the smart contracts of the logic smart contracts was not properly initialized, so an attacker could have deployed a malicious provider contract, which here would have been called through delegate call, and through delegate call you can essentially force self-destruction of the calling contract, which would have ultimately disrupt the system. So, like, one of the things that interested me when I started working in smart contract development was, okay, how does NASA handle this kind of mission critical software? And the interesting thing is that the process they define, they start not from, like, when I started first reading, I would have guessed they would start from the testing, but they actually start much earlier. They start starting by defining coding standards and best practices. So you start catching bugs not when you test, but when you actually write the code. So it's the way you write the code that helps you catching the bugs. So here I put, like, this is the table of contents of one of the main pages of the engineering handbook of NASA. Some of these steps are, honestly, can be directly translated to smart contract development. Some of those, like, I don't know, resource over subscription, thread safety, some of those cannot be applied because of the nature of the technology, but some of these can be directly translated to smart contract development. I put the link of the handbook here. I put some, like, key points here that can be actually translated in a smart contract development. So identify and define clear software development practices. Fault detection, which is super important, like detect when your smart contracts are and when your code is supposed to fail, and properly handling these particular cases. In-flight software modification, which is kind of recalls previous bug of Compound, right? The way you handle code that is actually in production already, and how you should handle upgrades for improvements of the logic of these smart contracts, and safe transitions is also super important. Most of the smart contracts can be identified as state machines, and these state machines usually have some pre and post conditions. Evaluating pre and post conditions usually helps catching bad designs in your process flow and in your model that you are trying to develop. And also the testing, which is super important. Here we see a kind of standard process flow, unit testing, integration testing, regression testing, and so on and so forth. Some of the key highlights: careful definition of the unit tests, starting so how you define the software units and how you test them. integration by testing like the software units working together, formal testing using automatic tools and formally defined models, and NASA requires 100% coverage on critical paths. So this is quite interesting actually, because like this is a very debated point. Like some say that 100% test coverage is usually not useful. It's interesting because like NASA defines these 4 points here. Like most of the proponents that say 100% test coverage is usually not so useful is because like some code paths are really, really hard to test, and some of them might look trivial. But if you look at the way NASA classifies their coverage, in none of them, like they say, you can ignore because the code path is trivial and it's hard to test. No, absolutely not. Like, if you are not hitting some lines of code in your coverage, it means that either the code is a dead path, or deactivated code, or there is a requirement that is missing. But like they absolutely enforce 100% test coverage, even for trivial paths that are hard to test. So how do I translate? I will try to be as quick as possible. How do I translate these two concepts to smart contract development? Define internal code guidelines. In Aave we have, and in BGD as well, we have like an internal document that everyone should follow that describes how the code needs to be written. This can be as opinionated as you want, as long as the whole team agrees with it. And it's super important because this kind of brings makes the code more homogeneous, more easier to review and to test afterwards. Clearly define your failure paths in your contracts and handling them explicitly, so failing early and loudly. Plan for software modification accordingly, so validating the storage change. Clearly and define and validate state transitions, as mentioned before. And in testing as well, I really push, when possible, for test-driven development, which is not so easy to apply all the time, but is something that we strive for. 100% code coverage, plan of post-deployment, and defining invariants, which is super, super important when you need to planify your testing strategy, and also through automated tool like the Certora Approver, or through tools like Foundry, and so on and so forth. I think I am out of time, right? Okay, I'm okay. So I was faster than I thought. Okay, so here are the conclusions. So as I mentioned before, we should consider smart contract development as mission critical software. Unfortunately, this didn't happen often in our industry, especially during the last couple of years when we had the DeFi summer and everyone was deploying code left and right. And where most of the teams like to be as fast as possible, to get as fast as possible in the market, like they were essentially rushing the code to production, or maybe forking smart contracts without having deep understanding of what these smart contracts were supposed to do, which has ultimately led to unpleasant smart contract hacks. Preventing bugs is not only testing, but it starts even before you start writing code. It begins with proper planning, proper definition of your specification, proper definition of your invariants, and which ultimately help as well when you're going to planify your testing strategies, and essentially your approach to find edge case and find bugs. Team culture is fundamental, so everyone needs to stay focused on this particular topic. So this is something that is very, very important to promote. Like security first is very, very important to promote within the team, and everyone should try to follow this particular approach of writing code. So as I mentioned, plan for security and plan early. Start planning even before you start writing the code. to avoid unpleasant surprise later. And then ultimately, we need to learn to live with the fact that we make mistakes, right? That is unavoidable. So the goal here is not avoiding making mistakes because that is unavoidable. The goal here is to try and catch mistakes as early as possible in your development chain, right? So whenever you are able to catch bugs earlier and they don't hit production, you essentially have reached your goal. Okay, I think I'm done. I don't know. Okay. Yes, if anyone has questions, like I would gladly take them.
Kurt and Jared and Mark can come up.
Thank you, everyone.